recording. Oh, hello, everyone who's watching this recorded. It's a thinner turnout today. We just finished the midterm. It's Monday, the week after the midterm. I think it went well. We're going to talk about, in fact, I'll just put this up now. So announcements. So we just finished the midterm. Congratulations, everyone. I think that went well. Scores will be out soon, no later than Friday. I think we're done grading. We're doing analysis now. Mid-semester grade reports will be released later this week as well. I don't actually know what that is, but I'm assuming it's going to help you figure out what your grades are at this point. That'll be helpful. No homework this week. Wow, that's nice. A little bit of a break. Really surprising. Lab 7, we still have a lab. Okay, due Friday at 11 p.m. Professor Sahai's office hours are on Zoom today from 4 to 6. And then my office hours this week are on Friday from 1:30 to 3 in 773 Soda. We're on Zoom for those who want to attend virtually. All right, so we're halfway through the semester. Hopefully people are feeling okay, maybe, about the course so far, the midterm. Again, we'll find out more, but congratulations. You've gone through, in my opinion, the more interesting, challenging setup of this class. And now we're to get to do the fun stuff. And so that is what today's lecture is about. Today's lecture is called Confidence Intervals, which is a horrible name for today's lecture. I want to rename it. It should be called the Bootstrap. So when I teach this class, I get the lectures handed down for me, and I've promised the TAs I won't make big changes because when I do that, it breaks classes. So we're following the same lectures from before. But when I got this lecture, I'm like, yay, I finally get to teach what was really the lecture that created this class. So the Bootstrap method is sort of this foundational idea of we can use sampling to solve really hard problems. In this case, we're going to look at confidence intervals, but this is sort of the genesis of this class, this Bootstrap. So pretty exciting lecture for today. Questions? Made some announcements, talked about the Bootstrap. That is today's lecture. No? Okay. So before we get to Bootstrap, we have to start with something a little more simple. We're going to talk about percentiles. So percentiles are a way of describing kind of the extents of data. And you might have already seen percentiles if you've made a box plot in the past. You've asked maybe the median, that's a percentile. You've asked like these quartiles if you've taken a statistics class. So we're going to talk about this more general concept of a percentile, which will be useful in estimating confidence intervals. So let's do it. All right, so computing percentiles. All right, so the pth percentile is going to be the first value on a sorted list that is at least as large as p% of the elements. Starting with a dry definition, let me give you an example. So here's my list of numbers. I want to compute a summary. This is a percentile is going to be a statistic. The first thing I need to do to compute a percentile is sort my data. So I sorted my list of numbers. Now I can think of these numbers as each having a percentile. So the one here, 20% of the data is at least as large as 1, right? And then sliding over, 40% of the data is at least as large as 3. 60% of this data is at least as large as 5. Sorry. 80% of data is less than or equal to 7, least as large as p% of the elements. And 100% of data, least as large as 9. Percentile setup. Let's go through some examples. So if I want to compute the 80th percentile of this data, what is that? That is 7. Got it? Okay. Going a little quickly here. This is my percentile. This is my data array. We're going to use this function in a moment. So this was pretty easy. So 80th percentile, I take 80 over 100 multiplied by the length. That gives me the location minus 1 to get the actual location in the array. And that's going to give me this element. So 0, 1, 2, 3 is the 4th element in the array. If the percentile that I give you is not one of these 20, 40, 60, 80, then you're going to choose the next largest element. So 60. If I said something like 85, what am I going to pick? 9. If I said 50, the 50th percentile, also known as the median, that's 5. Got it? So it's larger than 40. The next element here is 5 percentiles. All right. So we're going to use code to compute percentiles. And again, this is a basic summary statistic. We're going to use it to compute ranges. We're going to use it to compute confidence intervals in a moment, but start the function. So the pth percentile of a set of numbers is the smallest value in the set that is at least as large as p% of the elements in the set. So function in the data science library that we've given you is called percentile. It takes a p, which is going to be a number between 0 and 100, and a values array, which is going to be the array of elements. It doesn't have to be sorted. The function will sort it and compute the percentile for you. I should say, this is the definition we're using in this class. If you use other libraries, sometimes they use a slightly different definition, and they try to do things like interpolating. We're using this definition because a percentile should always be a piece of our data. That's a assumption we're making in this class. And this definition is cleverly worded because if all of my data were the same value, I can still define percentiles using this definition. All right, I went a little fast. There are questions. All right, let's walk through an example. All right, so I posted an empty notebook and a non-empty notebook. And I'm going to try to use my empty notebook and fill this in as we go. All right, so here's an array. This is my data. If I wanted to manually compute a percentile, the first thing I would need to do is sort this data. So how do I do that? A couple ways to do this in Python. We can do np sort x. That'll give me a sorted array. Python also has a function called sorted. Excuse me, a sorted array. Sorted is going to return a list, so we're just going to work with np.sort. So numpy sorts my array. Okay, and I've written this little function here that's going to show me a table. So I've computed my percentiles, so multiply 100, taking the numbers from, we go from 1 to, it's easier to read, 1. Because remember, we're computing percentiles, we're not starting at 0. This gives my percentiles in my data. Percentiles. So if I wanted to compute the 55th percentile, how would I do that? It's a little bit tricky. This is why you wouldn't want to do this in practice. So I'm going to go ahead and work this out. So I want to compute the 50th percentile. So I'm going to take the length of my array times the percentile, p, divided by 100. And that's going to give me an index. Let's look at that. So that's 3.3. I need to round this because I'm going to go to the next largest thing. So np.ceil will take me to the next largest thing. And now that's the index if I were counting from 1. But we're computer scientists, so we count from 0. And that's an integer, or that's a floating point number. If I want to index stuff, I'm going to need an integer. And now I have an index. Okay. So that gives me the value for that percentile. Kind of dry. Sorry about that for the beginning of this lecture, but we need this function to be able to compute confidence intervals. So that's the manual way of doing it. Don't ever do this because it's error prone. For example, watch what happens if I put in 100. It's the 5th element. 0, 1, 2, 3, 4, 5. Good. How about the 0th percentile? That's the -1th element. It's unlikely to work. So using my code here, I'd have to deal with this 0 case as special. So don't write code like this. Use the magic function we've created for you. So here's the percentile function. So this is just what I described earlier. So you take the p, a number between 0 and 100, and my array, and it'll compute the percentile for you. So you don't have to think through all this stuff. Okay, so click my table again. And my percentiles, there we go. So if I want the 50th percentile, it gives me 28. If I want the 55th percentile, what's that going to be? What number is that? So I think it's going to be 34. Yep. So 50th percentile is here. So 55th is going to be the next one over. If I ask for 0, it'll give me the first element. So this is well behaved. And I ask for 100, what's that going to be? So 0 is the min, 100 is the max. Okay. Again, kind of dry. Everyone got it? Questions? Questions at this point? Okay. All right, so that's percentile. We're going to use this throughout this lecture. The 50th percentile is pretty important. That's the median. We're going to use that quite a bit. We have a discussion question. Let's just go through this. I know it's really dry, but just do it once. Okay, so I have this array, 1, 5, 7, 3, 9. Which of these statements are true? Take, I don't know, a minute and discuss this with people around you. Go. Maybe stand up, stretch, I don't know. Quiet today. Okay. Let's go through these. So I think I have it code here. My percentiles again, make it easier to answer these. All right, so true or false? Who says true? Who says false? All right, so why is it false? So I'm asking for, well, 0, that's a problem. That's a dead giveaway. Percentiles in this class are going to be numbers in our data. So that's definitely false. Okay, good exam question. All right, how about this one? 39 and 40. True? False. Okay. So 39 is between 20 and 40. We jump to the next. So it's going to be 40. So 39 and 40 should have the same value. True. And they should both be 3 the percentile. How about 40 and 41? True or false? True? False. Okay. I think you all are getting this. So maybe we can move a little faster. All right, percentile of 50. That's the median. Important number is 5. Is that correct? True? False? True, I think. Yep. So the middle of my list here is 5. Questions? Why is 2 true and 3 false? Okay. So 2 is saying the percentile of this array, the 39th and 40th percentile, are both the same. All right, so the way this works is if you pick a percentile that's not one of these, 20, 40, not one of the actual data points, we just go to the next one. So 39 is neither 20 nor 40, but the next one after 39 is the 40th percentile. So that's going to be 3. And then we said, is that equal to the 40th percentile, which is also 3. So it's 3. That's true. Whereas 40, we said, all right, so 40th percentile, that's 3, that's for sure. And 41st percentile, that's between 40 and 60. So in the next one, go 60 percentile, that'd be 5. That's false. Okay, I think we got percentiles. Can we finally get to the fun stuff? Estimation. Okay, so this is the cool part. So far in this class, we've been asking questions like, is this true? Is this hypothesis true? Which is it, the null or the alternative hypothesis? That's a very important part of data science, but another important part of data science is, what is the value of? What is the value of the GPA of students in this class? If I only have a sample, how do I answer that question? And when I give you an answer, what does it mean? Is it just that number, or can I do more? If you've read scientific papers, they go, well, we have confidence intervals, tell me a range of values. But how do those come to be, and how do we compute them? And again, what we're doing in this class is using something that I learned in graduate school, and we're going to use it as an introductory tool, which is amazing. So really cool stuff. So how can we figure out the value of an unknown parameter? That is the goal. So example, let's say the average GPA of all students maybe in the whole world, I don't know, all students at Berkeley, maybe you have a sample. So if you have the census, that is, if you have the entire population, this is easy. You just calculate it. No estimation, no inference. I have the value, right? So it's almost uninteresting. Calculate the parameter from the data that you have. But if you don't have a census, it's more fun. So you're going to take a random sample from the population and use your random sample to answer these kinds of questions. This is where we're going to use a statistic as an estimate. All right, so some quick terminology. The parameter is the value that you're trying to estimate. The statistic is the thing that you're going to compute on your data and then hopefully relate it to the parameter, right? So I might want to know what's the average GPA. That's the parameter for all students at Berkeley. The statistic, I take a sample of students in this class, not quite a random sample, but a sample. And I say from that statistic, what can I say? What would be a good estimate of the average? Right? So you might say for this class, I'll take the average GPA for the GPA for all the students that are in this class, and I'll use that to estimate. That is my number. And I think that's a good guess for the GPA at Berkeley. As a quick technical, no, I won't do it. Okay. Turns out the average is not always the best statistic, but we won't talk about that. All right. So if I wanted to estimate the average GPA, I'd take the average, say, for example, from this class, that's my statistic, estimate the average GPA for all students at Berkeley using that number. But it's a number, and we want to talk about a range, a distribution. Give more than just a number. That's inference. So let's do a demo. Okay, so we'll go through inference and estimation. All right, so for this lecture, we're going to use a pretty cool data set. So this is the San Francisco public data on compensation for public employees for the city of San Francisco in 2019. And for this class, we're going to assume this is actually the full census. In life, you don't often get access to all the data, but here we're going to assume, and it's pretty close to a full census of the employees in city of San Francisco. All right, so first question is, I want to make a histogram of the total compensation. So after the midterm, everyone's pretty good at this now, so we'll do SF histogram. And then what I want to do of total compensation, that's this column. So we have other things. We have like the type of job, we have the salary, we have benefits. Total compensation should be salary plus overtime plus benefits. So let's see what that is. Total compensation. Okay, let's make 100 bins maybe. All right, so that's our distribution of what people get paid. So what do you think? Do you think anything funny about this picture? What are two things you should see? I see a big spike at 0. We are paying people 0. That's a problem. We should investigate that. Also, 700,000. So our histogram tool will go out to the extreme, whatever data was there. Somebody is making $700,000 a year in the city of San Francisco, public employee. So let's look at both these extremes. So who made the most money? How do we do that? Good exam question. SF, sort, total compensation. And then I want to sort descending equals what? Someone help me. True, I think, with the total. All right. So who's making all the money? So you have people in the far right that are making a lot of money. And these are people in retirement services, managing the retirement pension probably. So important job. These would be kind of extreme points. And as we do analysis, we're going to try not to focus on these extreme points. We want to look at the center of this distribution. And a statistic we often use when thinking about the center of stuff is actually the median, because it's more robust. It's less sensitive to these extreme points. So we'll look at the median. Now, what about these zeros? What's going on the other end of the spectrum? So who's getting paid the least? Take this code up here. Who's getting paid the least? So I don't need to do descending equals true. I want descending equals false. That's the default value. Somebody's getting paid 0. Why would people be getting paid 0? All right, I have no idea. One explanation could be is these are jobs that have just been listed. When computing a salary, they might have just started at the end of the year or started in the new year, but their job was officially registered in the system the year before. So there are weird reasons we could have 0. We're going to remove the zeros to focus on the majority of this population here. So how do we do that? How do we do that? All right, so I'm going to compute min salary. So here's our idea. We're going to take people who are working at minimum wage half a week. That's going to be the minimum salary we're going to consider, and we're going to just drop all the records below that and assume those have some peculiarity to the way the city has actually entered that data. So how am I going to do this? Filter, another midterm style question. Come on, someone yell out. Where? Thank you. I've lost my screen, so what's next? I'll just do this blind. Salary? Yeah, so we did salary. Good guess. I would have done total compensation, but I'm going to stick with what was done in previous lectures. So salary, we'll use that as our filter point. We'll ignore the bonuses. And then what I want above. So how do I do that? R dot above min salary. Great. Cool, that ran. All right, good. We got rid of those zeros. So that's our data. We're going to focus on this for our analysis. We've set our bins here to cap out at the top so we don't have the extreme values. So this last bin over here has a few extra points. Okay, so that's our distribution. Now let's talk about, this is our population. So we can compute the median, taking our percentile function. The 50th percentile is the median. It's going to be our population. That is the parameter. That is the thing we hope to estimate. Now again, this is a ridiculous exercise because I already got the parameter, so we should just quit. We're done. But the point of this lecture is to show you what happens if you don't have access to the population. All right, so that's our population median. What's our sample median? Well, we need a sample. How can I take a sample of 400 from this table? How do I do that? Exam question. Let's do this. So SF, I'm going to use sample. It's a magic function. I want to sample, let's say 400. So I took 400 people at random from the payroll. And then how would I sample? Is this with replacement? If you were doing a study in the world, in the wild, how would you do it? Would I go up to you, hey, what's your income? What's your income again? It would be silly to ask someone the same question twice. So in practice, typically, we will say with replacement is what? False. We don't want to resample people. That's a sample. So that's a sample of 400 people. That's the histogram. Let's do it again. Will it change? Hopefully. Yeah, it's a different sample. Right. So every time I run this, I'm getting a new sample. This would be me going out and maybe walking to offices I've chosen at random to find a specific set of employees to get a good uniform sample of what their actual payrolls are. So if I didn't have access to the full payroll data, I could go around and ask people this question. All right. So now I want to know, what is the median of my sample? That's easy. I take this median statistic. I'm going to take the sample. I need a column from that sample. So I'm going to take the total compensation and compute the percentile. So 135,000 is the median. That's pretty good. And 135,747 was the true value. And I got 135,361. Pretty close. Is that a good number? What do you want? You want more than that. You want something that tells me about the spread. So that's what we're going to figure out now. Okay. That's our goal. Return to slides. I think we're about to get to the fun stuff. Okay, so the variability of our estimate. So one sample gives me one estimate. If I do this repeatedly, I'm going to get different values for each of my samples. So each of my samples could be different. So the big question is, how different would it be if I did this over and over? I allegedly have a demo, so let's go back over here. Okay, so the variability estimate. So I want to generate a sample median. How would I do that? I want to make a function to do this. You'll notice in this class as a theme, when we want to repeatedly do something, we're going to make a little function to do that. So I want to generate a sample. So first I want to make a new sample. Okay, this is going to be, how am I going to do it? I want to do the same thing I did before. So SF sample 400, and I want with replacement equals false. So in life, you don't get to do this, but in this class, we will. So we have the population. So let's say we were to sample it again, and then we're going to return the percentile, computed the median, the 50th percentile, on my new sample. And I want the column total compensation. Felt right? Okay, I got it right. All right, so this function, every time I run it, oh, this is bad. It's a bug, right? Sample size here. So every time I run this function, I should get a new sample. Okay, so new sample. So it's moving around. Right? And we'd expect that, right? Every time I get a sample, I get a slightly different value. So what does that look like? So we, again, theme in this class. So if we have something we can sample, let's do it many times and look at the shape of the outcomes of the samples. Okay. So how would I do that? This is my for loop. Whenever we see these for loops, so we're constructing new samples. So I break into 2 steps. So I'm trying to compute a new median. And I will do that by calling generate sample median. And I want to use 400. Good. And then I want to put this in my sample median. So how do I do that? Sample medians equals numpy.append. And I'm going to add to my sample medians. And I want to add what? My new median. Good. Run. Take some time, do some thinking. What's this going to look like? What do you think? Take a picture. So these are the medians. So I sampled from my population many times. Each time I got a new median, and I made a distribution of my medians. Well, there's the truth. It's pretty good, right? Each of my medians, if I were to repeatedly sample from my population, it's going to be a nice spread over the truth. And what's the spread here? So like 130,000, 140,000, plus or minus 5,000. So my median estimates from my 400 size sample are pretty good. What happens if I make my sample larger, sample more from the population? What do I expect to happen? Bigger samples means what? What? Take a look. I'm going to run it again. This time I'm going to sample 800 from my population. I have some code here. The details of this plotting code is a little complicated. Don't stress about it too much. I'm going to put the plot up. Okay, the yellow is my sample size 800. Blue is my sample size 400. Let's get a little more concentrated. That's what we expect. So I take larger samples, I get a better estimate of my statistic. That statistic gets closer to the true population. All right, return to slides. Okay, so that's what happens to different samples, but I want to quantify this uncertainty. How do I do that? So the estimate is usually not exactly right. How accurate is the estimate usually? That's a good question. So we want to communicate to someone, say, hey, I've computed this median compensation. Is that a good estimate? I took 5 people, so maybe not such a good estimate. I took 800 people. Okay, it sounds like maybe a better estimate. But can we give a better picture? Here, it was easy. We had access to the population, so we could check it. But that's silly, because if you had access to the population, you wouldn't be taking samples. You would just compute the value on the population. Okay. So where can we get another sample? How do we get another sample? So if you want to understand the variability in our estimate, we want more samples. So we could simulate, but we only have 1 sample. So I have the population. I only have 1 sample from the population. What can I do? We needed many random samples. We just took many to get that confidence, that distribution. Okay, so we can't go back to the sample, to the population, or we could, but it would cost time and money. So you have to go back out and ask lots of people, do the sampling process 1,000 times, and then you could say, here's what it's going to look like. But again, very expensive. And I saw no time, no money. It gave me an idea. We'll come back to that. So are we stuck? Are we stuck? This is the exciting moment. We bring in a new tool, the Bootstrap. Okay, so what is the Bootstrap? First, what does Bootstrap mean? Colloquially, in English. What is a bootstrap? Come on, what's a bootstrap? Someone has to be into fashion. Yell it out. It's on your boot. Yeah, so my boot doesn't have bootstraps. It's really disappointing, but I'll use this for demonstration purposes. Okay, so here's a bootstrap. The story, bootstrap, comes to pull yourself up from the bootstraps. Bring up bootstrap. So those are bootstraps. So the idea is that it's a colloquial expression that, if you could go over here and you just lift yourself up by the strap of your boot, you could go higher up. Of course, it's nonsense because you can't lift yourself up by your bootstrap, right? So it's sort of using what you have to do something you shouldn't be able to do. Bootstrap. Startups do bootstrapping, try to use the money they have to succeed. We'll use Bootstrap to use our sample to make sense of the world. I want to announce today that we should make a new hit single. No time, no money. no time, no money. So we sample at random from the OG sample. That is a bootstrap, by the way. Those are on TikTok. We should have a video about this. So something about estimating confidence intervals, no time, no money. All right, so this is the bootstrap. Exciting topic, a big idea. It was developed in the late 1970s, so pretty new idea as well. So it's a technique for simulating repeated random sampling from your data, from your sample. All that we have is our original sample. It's a really simple idea, which is large and random, hopefully. Okay. And therefore, hopefully, this sample represents the population. So remember, I have 400 people's median, or 400 people's total compensation. Kind of looks like the population. So we're going to sample at random from our original sample. That's it. What does that mean? Here's my population. I went out and I paid for a sample. I got 400 people's total compensation. I don't ever get to see this picture. That's a problem. So I'm going to take that sample and you know what? I'm going to pretend that is my population. I'm going to sample from my sample. I'll sample once, twice, 3 times, many times. Okay? So I'm going to resample from that sample. All these look pretty similar. In fact, they look too similar. So they should be resamples of my sample. How do I do that? How do I sample my sample? How would you sample a sample? Actually, yeah, how would you sample a sample? Someone tell me. Invent the bootstrap. Come on. No? Yeah, give me a guess. Good. Okay, sample proportions. So we're thinking about the statistic. This is going to be easier. Watch this. Okay, so I don't have access to population. I have my sample. I want to sample my sample many times. How am I going to do it? The bootstrap principle. I guess I'll show you in a second. All right, so resampling from the original random sample. That's the idea. OG sample. Sampling is like sampling from the population with high probability. We'll get to that in a moment. Doesn't always hold. All right, so I have to give a disclaimer briefly, and then I'll explain how all this works. So if I'm sampling from my sample, and I'm trying to compute something that's well-behaved, something that's not extreme. We talked about this in previous lectures too. If I wanted to know who makes the most money, that's not well-behaved, right? So if I keep sampling from my sample, first of all, my sample unlikely caught the person who makes the $700,000 in the first place. And then if I keep sampling from my sample, the chance I get that is not going to be great, right? So it doesn't really give me a good estimate. But if I'm asking something like, what's the average? What's the median? Something that's, you know, a summary of the whole population, representing the whole population, these techniques work really well. So generally works. Reasonable estimating parameters if the original sample is large enough, and the thing we're trying to estimate is kind of well captured, reasonably well captured in the original sample. All right, so key to resampling. Now I get to explain it. So from the original sample, we're going to draw at random sampling with replacement. So remember, when we went to the population, we didn't ask a person their income twice in a row. That would be silly. But here, we're going to sample from our original sample. And then once we pull a person out, we put them into our new bootstrap sample, we'll put them back in our original sample so we can sample them again. So people will be represented multiple times in the bootstrap samples. Okay, and we have to do this, otherwise we get the same sample every time because we need to sample the same size. So our bootstrap sample has to be the same size as our original sample. Okay? So the same size as the original sample. And we need that because we want to capture the spread that we would have gotten from a sample of size 400, for example. So that's it. Sample with replacement, same 400 from our sample. And then we're going to compute the statistic on that bootstrapped sample. And we'll do that many times. And that's going to give us an estimate for the thing we just did a moment ago, where we actually got to talk to the population many times over. So we can compute the empirical distribution of that statistic. So here's some rough code. So we take our random sample from our population. This is where you paid money and you went out and got some data. You have your random sample. Now you go to your computer and you're going to bootstrap that sample to generate many samples. Each time you compute a statistic on that sample, and then accumulate those statistics, and we'll make a picture. All right. So We'll make comments in a second. Let's actually do the bootstrap. All right, so bootstrap, here we go. All right, so I'm going to bootstrap a sample from my sample. How do I do that? This is where you'll see that this class was built around this idea. So watch this. I have my original sample was called our sample that I went out and paid for. The function sample by default does the bootstrap sample. So it's going to sample all 400, but it's going to sample with replacement. That's it. Number of rows 400. We just resampled our sample. Pausing here for a moment. Questions at this point? Sampling your sample. Making sense? Blank stares. How about online? Are there lots and lots of questions? Why is it quiet? This is supposed to be a little confusing. All right, well, we'll keep going. Bootstrap sample. I'm going to take my bootstrap sample. This is, again, 400 sampled at random with replacement from my population. And I can look at the histogram of that. That's another picture. If I take another sample, let's see, what does this look like? Another picture, another sample. So you have some variability. So I'm starting to see the variability if I were to resample from the population. But I haven't done any statistics yet. So I'm supposed to compute my percentile from my sample. So 132,456. That's my median estimate from the sample of my sample. Yes. Yeah, so if I have 400 people, yeah, but I want to explain this to you guys. This is really important and very confusing. I have a sample of 400. I'm going to take a sample of 400. So another sample of 400. And I go, that's different. You're like, why is that different? Because I did it with replacement. So when I pulled someone out and I put them in the other sample, I put them back in this one. Okay, and I could actually pull that person again, put them back in the sample, and they show up twice. And I think like 60-some% of your data shows up multiple times in your sample. You can actually analyze that using, rules of probability. So a lot of people show up more than once. That's how this works. Other questions? Okay. Yeah. Yeah, so why does this work? There's actually quite a bit of theory behind it, why this works, why it's typically taught in a graduate class. The intuition, and I think you basically have it, is that if I have my population and I take a sample and my sample is representative of the population, then resample, and I think it's a sufficiently large sample that really does look like the population. Resampling from that and then computing my statistic will show me roughly the variability of my statistic on multiple samples from the population. That's the basic idea. So I'm essentially simulating the process of going back to the population, but instead of using the population as my true, the thing I go to, I'm going to a proxy for it, an estimate for it, which is my sample. If you take a graduate seminar, there's some discussions on like what statistics you can do this for, how good your estimates will be, how quickly they converge, and so on. We're not covering any of that in this class. We're just giving you the intuition, the basic tools. The bootstrap is a very powerful technique. You can go ahead and use these techniques, again, given reasonably large samples and things like medians, means, things that are well behaved. This is a very useful tool for estimating things like confidence intervals, which we'll spend the next few lectures on. If you like this method, and I hope you do, definitely consider taking graduate seminars and non-parametric statistics and learning about these kinds of techniques. Very cool stuff. Okay. So we had a sample. We took a bootstrap sample of our sample. So we resampled it, computed the median. So that was one bootstrap median. Let's make a function to do this over and over again and see what it looks like. See how well this works. Okay. So I need to construct the bootstrap sample to construct the bootstrap median. How do I do that? By now it should be pretty straightforward. SF? No. What do I sample from? Our sample, that's right. Don't go back to the population. You don't have access to the population. Except for today, we're cheating. Okay, I'm gonna take a sample, just sample. That's it, done. And then I'm taking the percentile of my bootstrap median, or bootstrap sample, taking 50 percentile. Cool. And then we run this. Now we get to see some variability for the different medians we compute. Right. So if we run it once, run it many times. I put this on one line. So I take my bootstrap medians and I'm adding one bootstrap sample at a time. And I'm going to do this 1,000 times. Okay. Take a look at what this looks like. So these are my bootstrap estimate of my sample medians. These are all samples of my samples. That was a true value. You don't normally get to know that, but we knew it today. And it's got a pretty good coverage of what I would see. And in fact, this looks similar maybe to the estimate I had up here, right? Get an idea of the spread. So again, 130, 140, a lot of our data is in that range. Let's see. 130, 140, a lot of our data is in that range. Not perfect. And I'd get a different picture if I had a new original sample, right? Questions? Okay. I thought this is a little bit new. Again, hopefully the TAs don't kill me for doing this. I'm going to actually work through, here's the program for Bootstrap. Here's a general thing called the Bootstrapper. Good name. So I want a sample. That's my sample I'm going to take in. That's the thing I bought. A statistic. This can be a function I'm going to pass in. This is going to compute my statistic on my samples and how many times I want to do it. Okay. So the trick to Bootstrap is first, build your Bootstrap sample. So what I do, I take my sample, sample, sample my sample. That's my Bootstrap sample. And this would be a good song. All right, Bootstrap statistic. How do I compute that? Statistic of my sample? No. Statistic of my Bootstrap sample, this guy. Okay. And then I want to accumulate these. So Bootstrap statistic to my stats, and I'm going to return them. Let's see if this function works. So I'm going to take my, let's do it. So I have a new sample. It's my OG sample. I'm going to sample from my population again. Went out and bought 400 people's total compensation. I'm going to define my statistic function called compute median. Takes a sample, computes the median of that sample in the total compensation column. And now I'm going to use my Bootstrapper function I just implemented. Take my OG sample, my compute median, and then I want to run 1,000 Bootstrap samples. Bootstrap medians again. Every time it's a surprise. Does it work out? Yeah. Okay. So that's another picture of what it looks like. Sometimes this is not going to be very good because remember there's chance involved here. Let's run it again. Maybe I'll get unlucky. Yeah. Sometimes the spread's not great because likely my original sample wasn't great. And then so I'm going to get some more spread. It may not perfectly align with the original median. In a moment, we're going to talk about computing confidence intervals from the sample. And hopefully most of the time, we'll be able to control that, our confidence intervals will contain this thing. Questions? Why didn't I say with replacement equals false? Good question. Yeah, so let's, oh no, let's come back 1 second. All right, so if I do OG sample dot sample question mark, so the sample function of my OG sample has with replacement is true by default, right? So I don't need to say anything. And if k is none, it just equals number of rows. If I tell it nothing, the default behavior of sample is to construct a Bootstrap sample. I have a bug. Yes. Do others see my bug? There's a bug. Fix it in the lecture notes. I went out and paid for 400 people from the population, but I said, you know what? Go ahead and sample people twice. No big deal. Now, so I went with replacement equals false. I'm going to pay for the sample. Let's get new people. Good. So my original sample with replacement is false. And then my subsequent samples, when I do the Bootstrap, I have to do it with true. Good catch. Another sample. Other questions? Yeah. Right. So when I construct my original sample for my population, because I'm going to pay for people to answer my question, I want to set the resampling to false because in the real world, you don't get to go to the population and say .sample. In the real world, I go out and say, hey, I'll pay you some money, or come into my survey, and I'm going to ask you some questions, and I don't go get back in line and do it again, because that would be crazy. So in the real world, I'm going to sample with replacement equals false, except I'm not going to say dot sample. I'm actually going to literally walk out and do the work. But then when I go to the Bootstrap, I'm back at the computer, I have to use with replacement equals true, because otherwise the method doesn't work. And it doesn't work because if I keep sampling 400 people with replacement equals false, every single sample will be the exact same 400 people. So I won't get any of that variability that I'm looking for. Other questions? This is a profound technique, so it's okay to be a little bit confused. Yeah, go through the slides. Yeah, let's keep going. But do ask questions if you have questions, please do. All right, so we've talked about how to build these Bootstrap samples. We've computed statistics on the Bootstrap samples. We made pretty pictures, but people don't want pretty pictures. They said, hey, what is the income? And you go, the total compensation, you go, here's my number. And they go, how good is it? And you go, here's my pretty picture. You're like, what does it mean? So what do people really want is a confidence interval. They want to, well, with some confidence, give me a range of values you think that the income is in, right? It's kind of the idea of this confidence interval. Who's seen confidence intervals before? Some of you have. Have you seen it with the Bootstrap? Cool, so a few people seen Bootstrap. Normally we compute confidence intervals in our high school statistics. And in fact, in my undergraduate statistics was all, you look up the special equation, you make some normal distribution assumptions, and you get some numbers, right? Those make a lot of assumptions. They won't apply to more interesting statistics in general. This will. So I'm going to show you the confidence intervals computed on the Bootstrap are something you can apply much more generally. This is why we use the Bootstrap. We want to compute a 95% confidence interval. So today I'm going to talk about how to compute it. And then next lecture, we'll talk about how to understand what it means. All right. So a 95% confidence interval, it's an interval of an estimate of the parameters. So based on random sampling. So I want to give you a range of the values that I think the median for this population could be. And 95 is the confidence level. So it's sort of implying that 95% of the time, 95% of the time when I do this resampling procedure, this interval will contain the population median. It'll be any percent between 0 and 100. You pick it. If you make it bigger, wider interval, which goes, yeah, the median income could be anywhere between 0 and 700,000. Not very helpful. You could make it smaller and smaller, but then you're not sure. So it's a trade-off that you have to make, just like this p-value cutoff from before. So higher level means wider intervals. Smaller value means smaller intervals, less confidence. The confidence is in the process that creates the interval, the sampling procedure. So it generates a good interval about 95% of the time. So let's do a demo, and then next week we'll dig in, or next Wednesday we'll dig into it some more. All right, so I want to compute a 95% confidence interval. I can actually choose where I put my lower bounds, but typically we try to center our confidence intervals based on our distribution. So we go back up to this picture, and I kind of want the bar here that contains 95% of the data. Right? And I want it to be centered on my distribution. So how do I do that? I'm going to use my percentile function. So am I computing the percentiles of? This is where it gets a little more interesting. What am I computing the percentiles of? Let's go back up here. I have my Bootstrap medians. Let's use this one. So Bootstrap medians. That's the samples I took, and I want to compute a 95% confidence interval. I'm just going to take the percentile. I want 2 point what? I just deleted it. 2.5 of my Bootstrap. Did I paste it? Bootstrap sample. Nope, Bootstrap medians. That's what I want. Okay. So 2.5. So it's saying take all my data, find the 2.5% in on the left side. And on the right side, I want to do the 97.5 percentile, 97.5, my Bootstrap medians. There we go. Array. My confidence interval. Why did I choose 97 or 2.5 and 97.5? Because the difference between those two is 95% of my data. What does it look like? Do you think I captured my median? Did I get it right? Yes. So that's my yellow interval. It happens to, I got lucky. The median, I expect to be lucky about 95% of the time, but I got the green point, which I don't normally have access to, is at the center, or is in my interval. So it is a good interval. Right. So rather than telling everyone, hey, here's the median for my sample, I say, here's a confidence interval. That communicates a lot more information about what the median could be. It captures my uncertainty that comes from my sample. All right. So that is the end of the Bootstrap. Tomorrow or Wednesday, we'll dig into interpreting these confidence intervals. I hope to see a song on TikTok soon.